In this video we're going to start our derivation of the Fourier series. Now I've split this into 3 videos so we can just keep the videos a little bit shorter. Now the idea of the Fourier series is a method of approximating a function using a series of other functions. Now we've seen this in the previous video when we looked at the Taylor series, so what we're going to do is just look at a little comparison with the Taylor series. So in the Taylor series we noted that we can approximate a function f of x by using a series of polynomial functions. So we said that f of x would equal the sum from n equals 0 to I of a n x to the n, and there would be an error which is your epsilon. So we know these values x to the n, these are just our polynomial functions, so our constant function, our straight line, the x squared, the x cubed, x to the 3, x to the 4 and so on. But we didn't know the values of an, and you can remember whenever we were messing about in the graphical calculator trying to guess the values of the an. But we found a method of finding the ans. So we have a similar idea whenever we're dealing with the Fourier series. We're approximating a function using a series of other functions. The only difference is now is that we've got a different set of functions. We're not using the polynomial functions in order to create the approximation. We're using the trigonometric functions, the sines and the cosines. So you might ask yourself, well, why bother? Well, the Taylor series isn't very good at approximating certain types of functions. So functions that have got any jagged edges, something we call jump discontinuities. So for example, square waves or triangular waves. But the Fourier series is very good at approximating those. So let's go ahead and we'll have a little look at the Fourier series and we'll see what it looks like. So this is the Fourier series written here. Now this is very similar to the Taylor series. All we're doing is approximating a function f of x using a summation of basis functions. In this case our basis functions aren't the polynomial functions like the Taylor series. The basis functions are the trigonometric functions, the cosine and the sine. So our contention is that we can add up lots of different cosine and sine functions and approximate this other function f of x. So as with the Taylor series, we know these values cos nx and we know the values sin nx. But we don't know the coefficients an and the bn's, and we have to try and find a method of working out what those coefficients are. Now I've drawn down the basis functions here, so that's our cos nx and our sin nx. So if we assume our n equals 1 there, then that's just the cos x function and that's just the sin x function. Now there's 3 ways that we can modulate or change the sinusoidal functions. We can either change the amplitude and just make it taller, so stretch it in the y-axis. Now we do that just by multiplying the values cos nx by our an, so that just changes the amplitude. And the same with the sin nx, the bn will just change the amplitude of this. Now we can also change the frequency, but the frequency is changed in a very particular manner when it comes to the Fourier series. We only use integer multiples of your base frequency. So let's say this is our base frequency here, so let's say that's 1 Hz. Then we can only use other cosine functions which are say 2 Hz, 3 Hz, 4 Hz, 5 Hz, so they're integer multiples of that frequency. The same with the sin nx. Now there's one other way that you can change the trigonometric functions. You could change the phase. So you could say, well, I actually start from a different point. But we don't do that with the Fourier series. The phase remains the same. So our contention then is that we can approximate a function f of x by adding up lots of sines and cosines which have got different amplitudes and have got different frequencies, but the frequencies are only integer frequencies of your base frequency. Now we're going to go ahead and we're going to look at some of this in the graphical calculator, and some of it will maybe become more understandable when you see it physically. So let's look at the Fourier series in the graphical calculator. Now you've got access to this file here. You just click on the resources section, there's a link that will take you through, and I do suggest that you open this up and have a little play with it, because you will learn quite a lot and it's quite fun. So it's split into three sections here. We've got the basis functions, the square wave and the Fourier series. So the same as we did with the Taylor series, where we had our basis functions which were polynomials, we're going to go in and we're going to look at the basis functions here for the Fourier series, which are the trigonometric functions. So the first part of our approximation was just a constant term. So there's a constant term there, and it's just a number. So that's our very first approximation to our functions, and it's the same as what we had seen in the Taylor series. But now we're going to look at the other basis function. So the other one is the a cosine x. So that's the cosine function there. Now the trigonometric functions, we can change the amplitude. So the amplitude in this case is a. So a is actually down here just below. So I'll get rid of my screen, okay? So you can see that a is just here. So we adjust a, we're just changing the amplitude of this cosine function. We can also change the frequency of the cosine function. So the frequency is a value of n. Now notice that n changes, and I've set it up so n changes from 1 to 10 in steps of 1. So it's discrete steps that this changes in. So you'll see that the frequency changes at twice the fundamental frequency, 3, 4, 5, and you can see it just changing that in integer multiples of that fundamental frequency, and that's it back to 1, which is the fundamental frequency. Now there's one other way you can change these functions. You can change it by adding on a phase shift, and I'll just show you the phase shift just now. So you can adjust the phase, it just moves it left and right. But as I said, whenever we're doing our Fourier series, we don't adjust the phase remains fixed. Now we can do the same for the sine. So that's our sine function there, and again we can change the amplitude of the sine function by changing the values of our b's, and we can change the phase of the frequency by changing the values of our n, and that is an integer multiple of a base frequency. Okay, so that's us looked at all of the basis functions, and our contention is that we can add up a whole series of these sines and cosines in the constant term as well, and they'll have all different values of amplitudes, and the frequencies will be integer multiples of a base frequency, and by adding all of these up we'll be able to approximate another function. So what other function are we going to approximate? Well, the kind of typical one would be a square wave, so let's draw out the square wave. So this will just draw the square wave for us. So you should definitely go through this process, download this and give this a go yourself. So that's the square wave there, and our contention is that we can add up all of those sines and cosines in order to generate this square function. So I've actually drawn out the Fourier series. You click on the Fourier series there, I'll let you see, and I've picked out the first 5 terms. So you can see here we've got an A0, and we've got our A1, B1, A2, B2, A3, B3, A4 and B4, and we've got our N1, N2, N3 and N4. So whenever we did the Taylor series, we noticed that, say, the first 12 terms, we would be looking for 12 values, so we'd be looking for our A1, A2, A3 up to A12. But in this case here, we've got a lot more variables here that we can play with. So we're looking at the first, in effect, 5 terms. If you count A0 as the first term, then the the A1 B1s is the next term, and it's A2 B2 up to A4 B4. So if you count all of those up, we've got 4 A's, we've got 4 B's, and we've got 4 values of n, and we've also got our constant term, so that's 13 values that you can change. Now we'll go ahead now and we'll just make a guess at it, okay? The same as we did whenever we looked at the Fourier, the Taylor series. So whenever I click on this, I've already got just random values in. So this here is the summation of all of those sines and cosines. Now you can just play about with this yourself, and you can see that we've got 13 of these that we can adjust to try and approximate this square function. So the chances of you adjusting these 13 and randomly coming up with your square function are pretty slim. But it's good to again just mess about with it just to see what kind of functions you can generate. So our contention then is that we can add up all of these functions, and we can, the sines and cosines, generate a square function. But all we're doing is guessing at it here. What we want to be able to do is find a mathematical method of finding all of these coefficients. And that's what we're going to do over the next couple of videos. So I hope you enjoyed this, and I hope it was of use, and I'll get you in the next video. Okay, goodbye.